And I'm also happy that so many people are interested in. And before I will start to talk about NMR relaxation and experimental requirements and model assumptions, I would like to thank Danuta, Gianni, Pedro, and all the other guys for making this possible. And I hope also that um, all you guys are in good health, which is really important these days. So I have one motivation today for you, and this is what is written here. So I would like to underline that fast field cycling relaxometry is a powerful method for the determination of coupling parameters as well as rotational and translational dynamics. However, we need suitable models for that, and they are required for evaluating properly the dispersion curves. And thirdly, molecular dynamics simulations can really verify the model assumptions we have for evaluating the fast field cycling data. And I would like to give you a couple of examples which shows that it is good to use simple methods, and sometimes we need to use the simple methods because we don't have lots of data, or the sample starts to freeze and we have only a very narrow liquid range. But in the end, we need to have reliable models to be sure to get proper coupling parameters as well as correlation times, right? And I would like to start very simple with a nice, beautiful paper, from 1948, so where Bloembergen-Purcell-Pound discussed relaxation effects in nuclear magnetic resonance absorption. And they came up with these simple equations, right, for the relaxation rates, 1 over T1 and also 1 over T2 as well. And they could dissect the two contributions into a coupling parameter, C1, right, and the spectral density part, including the dynamics and the correlation times. And of course, in this particular case, the relaxation rates can be frequency dependent, right? I would like to note that there's a coefficient not exactly right, but that's not important for our purposes. And Bloembergen-Purcell-Pound, actually it was Bloembergen in his PhD work, if I remember that correctly, who wrote down all these beautiful equations. So here we have T1 and T2 plotted versus the correlation time, or in other words, versus the inverse temperature, because we have a correlation between the correlation time and temperature via the Arrhenius relation. And you see this nice Debye-like behavior, but what they wrote down in the figure caption already, you see that everything is according to the simplified theory in which all interactions are assumed to have the same correlation time. So we have only a single correlation time. And I will show you today some example where this assumption is not justified. Although we tend to use this simple model for different reasons, right? Okay, so this is a picture we usually have if the VPP model is valid, and we have a single correlation time, isotropic rotation. So the behavior I've shown you before, but now for the relaxation rates expressed by the spectral densities here, we find this nice curve in the left side of the figure. So we're starting in the extreme narrowing region, where the product of the frequency and the correlation time is much smaller than 1. And then we have a maximum where the product is approximately 1. So if we can reach that, we can calculate the correlation times if we know the frequency of our instrument. And then to the right side at very low temperatures, then if we are lucky to reach the low temperature region, we can get the information where the product is much larger than 1. So to the right, you see the diagram we know from field cycling relaxometry, where we can where we can cover a large frequency range then, and are also happy that at higher frequency we can eventually reach escape the extreme narrowing case. So then we don't have a flat curve anymore and get additional information, because only if we have large enough correlation times and high enough frequencies, we can get this relation as shown, this equation as shown on the top. And then we are also able not to get some information about the dynamics, and but also about the coupling parameters, which is simply called C in this particular case. And this coupling parameter is always very important. And if something doesn't fit, people tend to move all the problems into this coupling parameter, but not discussing the proper value of the coupling parameter. I will show you how that can happen later on. Another thing may be of interest to you as well, if we come later on to real systems and relaxometry. We also assume that we cannot decouple the correlation part, the rotational part, and the structure part expressed by the coupling parameters. We also assume that, let's say, for a particular temperature range, this coupling parameter is constant, right? And in most of the cases, this assumption is justified, but not always. In particular, for the systems who undergo hydrogen bonding, this is certainly not true. So I give you a few examples. For water, for example, we know that the OH bond distance is 94.5 picometers in the gas phase, then 89 in the liquid phase, and 101 in the solid in ice. So that's a difference of about 6 or 7 picometers. And you see the coupling parameter, if you take it to the square, then we have R up to the 6. So that can make a difference. So we cannot assume always that this coupling parameter at least is always constant. But I will give you an example later on that we can be on the safe side by making these assumptions for most of the systems. And the same is true if we switch from the dipolar relaxation to the quadrupolar relaxation, right? Then the relaxation rate is proportional to the square of the coupling parameter, the quadrupole coupling constant. In this particular case for water, of course, we take the deuterons. And also here you see that they are very sensitive to hydrogen bonding, and that they vary between the gas phase and the solid phase about 50% of the value, right? So if you take 200 to the square or 300 to the square, you have a difference, more of a factor of more than 2. And that automatically means that also the correlation time, the dynamics is not described properly. Okay. So already long time ago, so here's a nice piece of work by Heiner Versmold, so 40 years ago, published in the Berichte of the Bunsen-Gesellschaft, Physical Chemistry, so a journal which doesn't exist anymore, but anyway, there are some really relevant also NMR papers in there, and he tried to get the correlation times for simple methanol, right? And the first problem can be here that even if you go down in temperature, methanol is still very fluid and you cannot reach the dispersion region, and you have to think about how to solve this problem. So here they added a little bit of D2O so that they were able, you see that in figure 3, so that they were able to reach a dispersion. Not that deeply, but they were able to do that. And then they fitted everything with a simple Bloembergen-Purcell-Pound equation, as I give you on the slide at the bottom. And what you should focus on is they got a quadruple coupling constant, deuteron quadruple coupling constant, a value of about 172 kilohertz. And they already knew that this is smaller than the solid phase value of about 192. And that is usually never the case in hydrogen bonded systems, that the liquid phase value is smaller than the solid state value. So they noticed already, in particular, if they compare everything to water, they noticed already that there must be something wrong. And they wrote, I put that into the red frame here, that the calculated value of 172 kilohertz must be considered as too low by about 20%. This might be taken as an indication that the reorientation of the OD group is not completely isotropic, right? So they already suggested that anisotropic motion has to be taken into account to get proper dynamics and also to get proper coupling parameters as well. Okay, and I would like to make some suggestions how to tackle the problem and maybe how to solve the problem, not only for these cases, but also for the dispersion curves where we perform measurements as a function of frequency. Okay, so this is what we all know and what you can read in a lot of review papers and nice articles by Danuta and Rösler and Stapf and many others. And I would like to suggest also to look up all these old NMR papers from the 60s and 70s, because most of the things are written up there already. So you can go into the store and can pick up the right and appropriate and suitable equations for your purposes. So the spectral density, of course, has a Fourier relation to the correlation functions. So G of tau, and only if G, you see that in the second line, is mono-exponential, and we have nice isotropic behavior, and the dynamics is described by a single correlation time, we get this spectral density as seen to the right in the first equation. But of course, we know that life is not easy, and that the correlation functions, they include both information, so the structural part and the dynamical part. And so for the dipolar case, of course, it's a vector described by the two nuclei interacting with each other. And in the quadrupolar relaxation case, of course, it's the interaction between the main component of the electric field gradient tensor and the nuclear quadrupole moment. And this tensor, of course, is time dependent, and that is all. And that is all written in the brackets in this elements of the time domain second ranked reducible spherical EFG tensor to the bottom, right? I will come back to that later, and I don't want to bother you with this more or less complex equations. I only want to show here, because these correlation functions, they are accessible by molecular dynamic simulations. So in molecular dynamic simulations, you don't have to assume a particular model. You can get the correlation functions and the correlation times and right away, whereas we as experimentalists, we have to rely on a suitable model, and I will give you some examples later on that some model assumptions are appropriate and some others are not, and how to fix the problem. Okay, so let's start with a very simple case. So we don't like that at all. In particular, if we perform fast field cycling relaxometry, it can be that we have substances, that we have material, that we have liquids that are very fluid. So we don't see any dispersion at all, and we still have to be in the extreme narrowing region. And then we have the problem, of course, the brackets, they simplifies to a single correlation time, that's fine, but we have only the measured relaxation rate, but two unknowns. So we don't know the correlation times, but we also don't know and don't have an idea about the coupling parameter, right? And so this situation can happen to you as well. So sometimes it can be that you don't see any dispersion, let's say at higher temperature, and only at very low temperature, dispersion behavior shows up. And then it's very helpful to have a good suggestion for the coupling parameter, where you start with if you try to fit your equations. Okay. So we start with the situation described here for the quadrupolar case, right? You see that we are still in the extreme narrowing as indicated by the thick red line here in both figures. If we measure everything versus the correlation time expressed by the lower temperatures then, or as a function of frequency. And if you have deuteron relaxation, you all know that our gamma is very small. It's only, so it's 6.5 times smaller than the gamma of the proton. And that means that we usually are in the extreme narrowing and we never reach really dispersion. But anyway, it's still interesting to know what the coupling parameters are. And we tried to do that long time ago. Actually, I did that in my thesis, so it must be a long time ago. And we used, let's say, for water, the 017 method suggested by Leiter et al. So we have fast proton exchange in water, and to get some dipolar information, we used differently 017 enriched samples. And from extrapolating everything to 100% O17, we could dissect the pure intramolecular relaxation rate based on the interaction between the proton and the O17, right? Whereas all the other part is an average basic proton-proton relaxation. But this way, then we were able to get proper correlation times for the OH vector in water in such a way. But you see also in this equation here, we still had to assume that the coupling parameter here, the OH bond distance, is constant. And we see later on for other examples as well that in first approximation this assumption is justified. But this way then you are able to get the correlation times. Of course, that's a very expensive approach. And for your complex systems you are usually investigating, you cannot use this approach, right? For example, if you have nitrogen in your system, you could do similar experiments by varying for N14 or N15, but that's costly, and so it's related to blood, sweat, and tears. So it's really tough. It's really tough work, in particular if you have to do the synthesis, as I had to do during my PhD work, being a physicist. So that was not that easy. So there was Mark Wendt and Tom Farrar who made a nice suggestion. And what they did here, and I applied that here to the water, to get an idea about this coupling parameter, right? They plotted, they calculated simple small water clusters and calculated the deuteron quadruple coupling constants and the proton chemical shift versus TMS, like in the experiment as well. And then you get a nice relation, which is more or less linear in this particular case. So if you are close to 0 ppm chemical shift, the coupling parameter is high and is close to the gas phase value, which has been measured by microwave studies. And if you then increase your cluster size and increase hydrogen bonding, then you get down, then you get downfield shifted proton chemical shifts, and also smaller deuteron quadruple coupling constants. So everything fits here. So what you can do now is you measure the proton chemical shifts, and that's a piece of cake. Let's say 4 ppm at a particular temperature. You go up, and then you can read immediately, let's say here 4, then you go to the y-axis, and you get a reasonable value for the deuteron quadruple coupling constant you can use. And this small square here I put in because that covers the change in chemical shift as a function of temperature for the temperature range between 0 and 100 degrees Celsius. And you see that's basically between 4 and 5 ppm. And that is related to a relatively small change in your coupling parameter. So the assumption to use a fixed or one deuteron quadruple coupling constant by evaluating, let's say, your equations is in first approximation really justified in this particular case. Okay, so to show that the both methods I just introduced are give similar results, I plotted the correlation times for the OH vector we obtained as a function of temperature. So these are the data here from the 017 methods, and the red squares are the ones obtained by Wendt and Farrar. So in this particular case, we only need to calculate, to measure the chemical shifts, get reliable values for the coupling parameter, measure the T1 deuteron relaxation rates, and we obtain the OH correlation times for water over the whole temperature range. And this method, I will show that later for ionic liquids, that is more or less universal. So you can use that also for, if you have the same functional groups, the OH function here in this particular case, it's more or less universal. So you can use it as a function of temperature. You can use it as a function of mixture, as a function of pressure. You only need the appropriate chemical shifts measured at these particular conditions. Okay. So I would like to show you now for more complex systems, that is ionic liquids, that are all involved in hydrogen bonding, that this is a suitable method before we come later to real dispersion curves. We have the first example where we have an imidazolium-based cation, where we have this very acidic C2 position here, for example. And then we have a triethylammonium cation. Of course, we have counterion for each system with different interaction strengths. But here we have hydrogen bonding via the NH axis. And in this hydroxyl functionalized pyridinium cation, we have an OH which is involved in hydrogen bonding, right? And of course, we have then HD exchange, and we are focusing now on deuteron relaxation rates we obtain for the C2H, for the NH or ND if you want, or OH and OD functional groups. Okay, so let's start with the imidazolium system. So here we have the SCN anion here, and what we did was what Mark Wendt and Tom Farrar suggested. So we calculated the coupling constants and the proton chemical shifts for a lot of different ionic liquid clusters. You don't have to do that for your system again and again or always new. So please look to the literature. There are some equations available, and the most important thing is really the functional group. If that is similar to your system, you can use it, right? So then we measure the proton chemical shift as a function of temperature and get reliable quadruple coupling constants, finally leading to these nice correlation times, right? In particular for systems, for whatever reason, I mean, here you could probably reach a dispersion as well at high enough frequencies. But in particular, if you are limited to the extreme narrowing region, you can get reliable coupling parameters and finally also reliable correlation times. So that was some older work. So this triethyl ammonium or tri-alkyl ammonium based systems, they are similar. So there we have the same situation. So we measure the deuteron relaxation rate, want to get the correlation time and have no idea, in particular for ionic liquids, none of these coupling parameters are known, right? We have no idea about the deuteron quadruple coupling constant. So we used again the approach, and here we have the same triethyl ammonium cation, but three different anions of different interaction strengths. So if we have weak interaction strengths, we have high coupling parameters. And if we have high interaction strengths, like for the methylsulfonate anion here, we get strong hydrogen bonding and thus finally low coupling parameters, right? So that's very convincing here. I think you get this nice linear relation. There's tiny differences here depending on whether you perform the density functional calculations with or excluding dispersion forces explicitly. But anyway, again, you can measure the proton chemical shifts for your NH and get a reliable coupling parameter. Of course, you see already that the coupling parameter must be smaller for this ionic liquid here, including that anion, compared to the NTF2 anion. So we, into this equation, we added also molecular liquids like N-methylformamate, N-methylacetamide, ammonia, for example. And what you see is, these are the data here we plotted here at very low chemical shifts here. And they nicely agree with the values, with the pair of both values experimentally known for the molecular liquids, right? So there is the same equation where they use molecular or ionic liquids. And then we simply measure the chemical shifts and come up with reliable coupling parameters for the liquid phase, okay? So these are the numbers, the coupling parameters we determined, and then with the relaxation rates here, we are able to come up with reliable reorientation correlation times for the NH or for the ND group here in the ionic liquid, which is always involved in hydrogen bonding to one of the oxygens in this particular case. So this system, for this system, it also works nicely. All right. And we could not be 100% sure that our suggestion from this method for the coupling parameters is real, right, and reliable. And then, so we asked our friend and colleague Daniel Kolokolov from the University of Novosibirsk at Akademgorodok to do some solid state experiments to get the coupling parameters from the peak patterns, right? And the result is shown here right away, that we don't have to go into more detail here. This is the values for the deuteron quadruple coupling constant we obtained for the liquid phase. And these are the data here we obtained from the solid state experiments. So what we can conclude here, we say the same trend with interaction strengths of the anion in the liquid as well as in the solid phase. And the solid phase values are, as expected, similar to what we observe for molecular liquids, such methanol or water, are smaller than the one in the liquid phase. So this method then gives you reliable numbers of the coupling parameters for the liquid phase. Okay, so the last example is here the one for the hydroxyl function of pyridinium or imidazolium or other cations. So this has been mainly done by Anne Strate and Vivian Overbeck here. So we have again this nice equation. It's a little bit more crowdy because we have data from a lot of ionic liquids herein. So it's basically this imidazolium cation here, but the function is similar as shown before. And again, around 0 ppm, we get gas phase values for the coupling parameter. And then if we shift, if we have stronger downfield shifts, that's related to a decrease of the quadruple coupling constant. So both the proton chemical shift and the coupling parameters are sensitive probes of hydrogen bonding, and they show this nice relation to each other, and that helped us to come up with the coupling parameters and finally with the correlation times for this OH vector, which is involved in hydrogen bonding to anions in the ionic liquids. Okay, so far we have the possibility by using this kind of methods to get a reliable coupling parameter. That's not only true for the deuteron quadruple coupling constant, that's also true for bond distances as well, just for the case that we are in the extreme narrowing. And very often we have to stay in the extreme narrowing because we have a small narrow liquid range, for example, and or the sample starts to freeze and we never get into the dispersion region. But even then, and here comes the point now, if we have a broader liquid range and higher viscosity and sufficiently high frequencies, we may be able to reach the dispersion, right? And then we tend, I did that, lots of other people are doing that as well. The data situation is not that great, but of course, what you are doing here is then fitting everything to the Bloembergen-Purcell-Pound model by assuming a single correlation time and isotropic rotation, right? And I will show you that this is not always justified and how you can fix the problem. So this is what we also, and why that is a problem. So we use this ionic liquid here, the triethyl ammonium triflate ionic liquid, and here are the data point we measured in red. There are bigger and smaller circles that depends on the frequency of the spectrometer. In one case it was 500, in the other 400 megahertz. And of course, we find this nice dispersion behavior. We are out of the extreme narrowing limit. But what we are usually doing, we as well, is to fit everything to the simple Bloembergen-Purcell-Pound approach. And then we get this dotted line here. And everything seems to be okay. People are usually happy. The fit looks nice. And then you come up with correlation times. But the problem here is, if you do this fit according to this equation, you obtain a quadruple coupling constant in about 110 kilohertz. And that is way too small. We have seen before that even that the solid state value is already about 150 kilohertz, and it's about 190 kilohertz in the liquid phase. If you assume these higher constants, which are suitable or reliable, then we get fits, other dotted line curves here, which don't have anything to do with the measured data anymore, right? And if you have, let's say, a coupling parameter, which is only half of the real one, and take it to the square, you have already a factor of 4, too low here at this structure part, and of course then correlation times, which are about a factor of 4, roughly higher than the real ones, right? So you cannot simply bury all the problems you have with these fits, even if they look nice, to this into the coupling, into a wrong coupling parameter finally. Okay, so what we already assumed here is, and everything was fine, we got a nice quadruple coupling constant if we assumed anisotropic rotation for the system, as shown here by the straight blue line, right? But of course, we haven't had any data supporting that, because we had to finish the experiments here because we had no signals anymore at low temperatures. Okay, so we switched the system by having longer alkyl chains here, and by using a stronger interacting methyl sulfonate anion. And then you see here that we were able to reach a maximum here, and then this fit by assuming anisotropic rotation is justified, and then we get reliable numbers anymore, whereas we don't get we get wrong numbers if we use a simple Bloembergen-Purcell-Pound pound approach, right? And of course, then you can get some information about the anisotropy and the tumbling angles and so forth. But this is what I don't want to go into detail here. I only want to say that even if things fit with a simple model, the correlation times don't have to be right, because the coupling parameter is wrong. Or to say it in other words, the distribution into the structural part and the dynamical part is not of the relaxation rate is not correct. Okay, so I would like to show another example we are still working on, or let me say it this way, we just submitted this work by Vivian Overbeck, and I would like to show you the main things here. So we could derive by fast field cycling and relaxometry the rotational correlation time, the overall correlation time here of this cation. Then we performed deuteron relaxation time experiments where we get the coupling parameter from the approach I just introduced. And for this system, besides the protons on the cation, we have also the 19 fluorine nuclei here on the anion to get some additional information about the motion of the anion. And I will come back to that later and explain in detail what we got out. And we would like to do that step by step. So that is a well-known dispersion curves you get for the protons and for 19F here, for example. And you can everything. We tried to evaluate everything as we are usually doing by using the Bloembergen-Purcell-Pound approach. So we did that for both nuclei, and we could dissect then the total relaxation rates as nicely published and written by Krug, Rösler, and others. So it's in a similar fashion here. Here in particular, we had two intermolecular relaxation parts, the ones between the protons of two different cations, and also between the protons of the cations and the fluorine atoms of the anion. So everything seems to be fine. So what do we get out in the end? That is the diffusion coefficients from the intermolecular relaxation rates by using this approach. And you observe that the cations are somewhat faster, have a slightly higher diffusion coefficients compared to the anion. But we really have a nice temperature behavior. And these are data here from the literature, which nicely fit at the higher temperatures to the diffusion coefficients we got from fast field cycling relaxometry. We also added here in this figure the data, the self-diffusion coefficients we obtained from our molecular dynamics simulations as well. And you see there's nice agreement at higher temperatures and a factor of 2 difference than at somewhat lower temperatures. Simulations at further lower temperatures are very hard to make because the system is already relatively high in these systems. But what we can state here is that the diffusion coefficients from this approach nicely fit to the diffusion coefficients obtained from the regular pulse gradient field experiments in NMR, right? So what about the reorientational correlation time? So these are the filled blue circles here, and that's the numbers we get from the intramolecular dissected intramolecular relaxation rates from FFC experiments. And what is nice to see here is that if we plot the relaxation times we get from the approach I introduced before, where we got a reliable deuteron quadrupole coupling constant from this Mark-Wendt approach, then we come up with this correlation times, and they are shown here in pink, and they nicely agree with the ones nicely agree with tau r from the fast field cycling experiments. So that tells us two things. So that the reorientation of this ND vector here describes the same dynamics as the overall relaxation of the cation. That means we more or less have one correlation time. So then this Bloembergen-Purcell-Pound approach is justified. And interesting here is also that we have two relaxation mechanisms we make use of, dipole-dipole and the quadrupolar relaxation mechanisms, and both lead to the same results, and both correlation times agree nicely. We also added, that may be important for later, we also added the molecular, the correlation times for the NH vector of the molecular dynamic simulations, and they also nicely agree with the experimental data. They are somewhat higher, up to a factor of 2, but for simulations and the approximations and the assumptions you have to do within your force field, it's very reliable. In particular, that we can nicely describe the temperature behavior, which is similar in both the simulations as well as in the experiments, right? So now we come to the part, the relaxation contributions for the anion, right? So describing then the interaction between 19F and 19F. And here, if we use the simple Bloembergen-Purcell-Pound approach, we come up with these yellow triangles here. And if you look then to the correlation times, they are much higher than the correlation times we obtain for any vector in the molecular dynamics simulations. And that can be. Instead, in the molecular dynamics simulations, we observe that for, let's say, the NC vector as a CC vector, the SN vector, whatever vector you choose in your cation, in your anion, these correlation times are about 5 times larger than the ones related to the CF or to the FF correlation times. So there's already the assumption, or that suggests that we have a kind of internal rotation of the CFC groups versus the molecule, and the molecule we assumed to be the slowest vector in the system, which has been the virtual CC vector here, right? And if we assume that, take, let's say, NS or CC as the molecular vector, and regard then the reorientation of the FF interaction or CF interaction as internal, we come up with reliable results, right? For the main slow vector describing the overall tumbling of the anion and the internal rotation of the CF3 groups here, right? And I think that's a nice example where you can show that it really depends on where your dipolar nuclei sit, whether they sit right in the center of the molecule, whether you have internal motion and your vector is sitting on a methyl group or on the CF3 group. That has to be taken into account, right? Very often people are using fits and come up with beta parameters being between 0 and 1. Of course, it's always justified to do that, but there's no real physical picture to my taste in these beta parameters. And very often you have simply not a simple correlation times, but internal rotation or anisotropic rotation, as in this particular cases. So my last example is we had published recently with our colleagues from Vienna University, Ottmar Steinhauser and Christian Schröder. So where we compared fast field cycling relaxometry data with molecular dynamic simulations. And as I told you before, molecular dynamic simulations get the correlation functions immediately. They know the shape, they know whether we have a single correlation or where we have a distribution of correlation times or where the correlation times are intrinsically not single exponential. And then we get an idea about FFC, the reliable values to evaluate the FFC relaxometry data. So we can really check the validity of relaxation models. So we have done that for this particular simple ionic liquid. So that's an imidazolium cation and dicyanamide as anion. And the good thing here is we could focus on the protons here only, because we don't have any reasonable NMR sensitive nuclei on the anion. So we could focus then on the intramolecular proton-proton interaction as well as on the intermolecular proton-proton interaction, right? So that was not a very interesting system, but we only want to show whether the model assumptions we are doing are fine and are justified compared to the simulations, right? And because you can calculate all the properties in your simulations and can simulate finally the relaxation rates, the dispersion curves, and you can compare them directly with what you measure. And then you have nice molecular insight. You get reliable coupling parameters, diffusion coefficients, as well as correlation times, right? So here it is shown on this simple picture, what we can look at. So the HH different distances, of course, in the simulations, they are well known because you define your molecule. And of course, all these intermolecular distances, you have to calculate them all and you weight them all and you find nice distributions. And as a function of temperature, you can get also from your simulations. So all the assumptions we have to make within our models to get somehow reliable or to suggest somehow reliable coupling parameters, they are given here. And if the coupling parameters agree with what we have in the simulation, then we can be sure that that's at least one criterion. Then we can be sure to have used the right model. Okay, so here is what you all know. We have the proton-proton relaxation rates, dissect them into intra and intermolecular part by using the Bloembergen-Purcell-Pound approach. What we also did, what Danuta and Rösler did as well. So we looked up the low frequency range, because in the low frequency range, only the intermolecular part shows dispersion. So from this approach, then we can get also the diffusion coefficients as well as from the intermolecular part as dissected here, right? And I will show you the results later on. Here is what we directly get if we measure the dispersion curves as shown here by the filled symbols. And the lines here, these are the data we get from the simulations by taking all the interactions with the geometries we have in the molecule and between the molecules, between the NMR sensitive nuclei. Yeah, we get that. And we have really good agreement. There's some assumptions made here, and because simulations are very challenging, in particular at low temperature, we could cover or measure more temperatures than our friends from Vienna could simulate, right? One point I would like to make here too is that we know all the intermolecular proton-proton distances from the simulations, right? And get average values. We know, and we also know how strong they contribute to the overall relaxation rate. Let's say here, the protons of the two of the different methyl groups. How strong do they contribute to the interaction? So it's about 8%. If we want to know what is the contribution stemming from the ring-ring proton interactions, that's 6%, and so forth, right? So we get really a nice detailed pictures. That helps us also for evaluating the data and for choosing the model and for assuming that's always a problem. So what kind of nuclei we have to take into account, right, at a particular distance. Right. Okay, so here are the diffusion coefficients as well as the reorientational correlation times. Of course, in MD, then you can address all different kinds of correlation times, and if they agree with those from relaxometry, you can also tell what is the main, or what is the slowest vector, or what is the main vector of the molecule determining the overall tumbling of the system. And of course, here in principle, we should observe internal rotation as well, which is here not that relevant because we have protons all over the cation, and that is different from the anion case where we only had the fluorine atoms on the CF3 group, right? And what you can see here also, and Danuta has shown for some examples in the past as well, that we have nice agreement between the diffusion coefficients we obtain from this low frequency region and that what we get from dissecting inter and intramolecular relaxation. So that looks fine as well. Okay, so let me conclude. So it's always good to have a broad frequency range available. Of course, we have up to 42 kilohertz by our nice fast field cycling relaxometer from Stellar, but sometimes it helps to do some additional experiments in your analytical department at higher frequency, only for checking or only for getting some coupling constants, which may be useful for evaluating the dispersion data. We showed here that we have two relaxation mechanisms, dipolar relaxation and quadrupolar relaxation, giving the same result. So that makes us also a little bit more confident in the coupling parameters we are using and the approaches, how to derive the coupling parameters. And of course, it's always helpful, as in this case, just shown, to have as much nuclei as possible, which are NMR sensitive. But the key question is really which molecular vector is addressed, where is the vector, and what kind of motion is this vector describing? The dipole-dipole vector or the main component of the electric field gradient tensor in the quadrupolar relaxation case. And then at the end, you can get reliable coupling parameters and correlation times and diffusion coefficients. And then fast field cycling relaxometry is really a very mighty method, right? And with that, I would like to end my talk, but I would like to say many thanks to Ottmar Steinheiser and Christian Schröder. So that is an ongoing, where we just published this paper about comparing fast field cycling data with MD simulations. That is an ongoing cooperation. And we just identified new and other systems which are more complex than the simple one we have chosen, where we mainly addressed the proton relaxation of the cation, leaving out the anion. And I would also like to thank Daniel Kolokolov from the University of Novosibirsk, Akadem Gorodok. That's also an ongoing. It's also an ongoing cooperation. We try to get these coupling parameters from solid state experiments and also dynamics in the glassy system down to very low temperatures to see how the coupling parameters and the dynamics of the systems behave there. And of course, I would like to thank my group in physical and theoretical chemistry. In particular, I would like to mention Vivian and Anne. They did the main work. Vivian built up everything, so they did the main work. I've fast field cycling relaxometry data I've shown you today. And of course, there are these great guys in simulation, namely Dietmar. He's not on this picture here, but he's joining us today as well. And for the last, or the second last example I've shown, Benjamin Golub did simulations. Of course, I'm in a happy situation because we have nice and friendly physical chemists, and we are doing experiments and simulations at the same time. And that is very helpful to get a really nice molecular picture. And at the end, I would like to thank also the DFG. They gave the money for buying the Stellar instrument, and we are now in the situation to make a lot out of it, and we try to work hard. And in the very end, I would like to thank you very much for your kind attention, and I'm happy to take your questions. Thank you very much.